I'd be talking about like if things are rotating. Well, obviously, you're spinning in the same spot. You're not going like left and right like we did before. We have a block sliding across the floor. We had a car or a plane taking off on the runway, moving forward or going to the left. Now, when things are turning, rotating, they're like, there's still actually something called position. Where's the position relation where it used to be? What about the velocity? But they're not called, it's called angular position, angular velocity, and angular acceleration. So we'll begin with angular position. So this is like the distance traveled. For that, we use the letter theta. So the four equations that we looked at in the first or second class, we use x for distance. Here, theta is going to be my distance. Now, things to, like, if you have an object that's rotating, let's say your bicycle wheel, there's the bicycle wheel, and we'll use this as reference. We take the wheel, we put a little mark on it. So right now the angle is 0. If you turn this up till that mark is right here, notice I marked the tire here on the bicycle, and I moved it in that direction. So this is the distance traveled. That's what theta is. And by the way, theta has to be in radian. Can't be in degrees. So we traveled from here to here. Is that clockwise or counterclockwise? It's also possible that you can take the wheel again, and there's the mark on it, and that's your reference, and you travel in this direction. So we use positive value if you do what? Counterclockwise. Counterclockwise rotation. We use negative values when it's clockwise rotation. At least that's our book used that. Now, as I said before, remember, theta has to be in radian. So you got to make sure you convert things to radian. In radian, a full turn, 1 revolution. That's 360 degrees, right? How many radian that is when you do full circle? 2 pi, yes. So a lot of times you are given RPM. What's the RPM stands for? Revolution per minute. You have to change it to radian per second. That's speed when we get to it, you know. If you took math, by the way, with us in tech math, we cover something called arc length. So if you know, for example, your theta, and you know the radius, you can find that distance traveled. That's called the arc length, S. S, which is the arc length, is equal to pi times r. I mean, r times theta, not pi times r. R times theta. Pi times r, where's that coming from?
You want some pie?
Yeah, I could go for some. I like pie.
What's your favorite kind of pie?
Any pie. Any food, any
Do you have
pie.
any pie you don't like?
There's not much food I don't like, to be honest with you. Yeah.
I don't like fish.
I'll eat fried fish. I will not eat, I can tell you the few things I will not eat or drink.
You want to go sample like sushi?
Oh, no. No sushi. But the one I will definitely will not eat is French onion soup.
What? That's so good.
Never had it.
amazing.
Never had it. Never will.
I haven't had it since I was 10 years old.
Smells like dirty socks.
But because I'm
That's actually
Nope.
really good.
Tastes good.
That's
I won't eat
thing-
it.
That's one of the like 2 things I miss being a vegetarian. Is like I hate that I can't have that soup.
No, not that. And I won't eat eggnog. Drink eggnog, not
Can't be
eat. But
friends. Eggnog
Yep.
is amazing.
I make
I know.
French onion at least once a week.
really,
I love it.
I love
It's
French
my wife and my daughter love
Cheese
it.
on top. Oh, that's and without the cheese, I'd be like, get out of here. But
Just think, somebody listening to us on this video now, they'll be going, French onion soup, what does that do with physics? Just to let you know, people listening to us, this is just a class, we're having fun. Yep.
you gotta have fun or you're going crazy.
So what about the angular velocity? Again, angular velocity, we use W for that. And it's the units for that is radian per second. Just like the distance, angular position, the unit for that is radian.
Again with the W.
Yep.
Yeah, I was gonna say.
And W, the angular velocity, it's the distance. Remember, speed is what? Distance over time?
Yep.
That's what is speed. So angular velocity is the angular distance, position, delta theta,
Yeah, work.
over delta t, distance over time. And just like velocity, when it's linear velocity, if you go in that positive x direction was positive, and backwards negative, we have the same thing. W is greater than 0 when it's what? Counterclockwise. Positive when it's counterclockwise.
So will it tell us that we have to put the calculator and
Radian?
we have to know?
No, you have to know. Yep.
On
They're not going to be that nice to you, no.
On the exam, are you gonna have the questions be like, this is from chapter 10, this is from chapter 2, or is it just gonna be a whole mix and we have to figure it out?
Actually
Or will
says.
it be like
it-
8.1?
No, it says,
and it'll be
yeah, item 1, item 2, item, that's how they're numbered.
Oh, it won't say like
No,
6.7.
no.
Could you make it that way?
No, it comes out that way. Item 1, item 2, item 3, actually. So let's look at angular speed and see what we have here. So again, for speed, how fast the thing is spinning. If this is your reference,
So the value is positive, the same as with the.
if you're spinning this way, W is greater than 0. If you're spinning this way, W is less than 0. We use negative value if you clockwise. We use positive value if you counterclockwise.
Why?
As somebody decided to go with that.
But it's opposite.
Yeah. Let's take an example here. Wheel of Fortune. Is that show still on there?
Yes.
They get a contestant, the person walks in, you grab it and they spin it. And they usually take and spin it down.
That's not Wheel of Fortune.
What is
That's
that?
The Price is Right.
Whatever that show, I know.
Wheel of Fortune, you have the
Oh no, well that too, one of them, but they spin. So the price is right, whatever it is, so you take the wheel and you spin it. Come. So it's gonna spin down usually. They have an arm that you grab it and you pull on it and they spin down. So if they're gonna spin down this direction, here we go. It's spinning at the rate of 17.0 RPM. The question, what is the angular velocity?
So there will be angular velocity, 17 RPM.
Yep. Now, every time I turn the TV, if that show was on, I saw the person grab it high and they pull down. So they spin it really in this direction. So W should be what?
Positive.
If you're going clockwise, W is what?
Negative.
Negative. Then they spin it down, it goes this way. So you're going clockwise. So
Clockwise
it,
is positive.
clockwise is negative.
God damn it.
Clockwise, positive,
Yep.
negative, counterclockwise is positive. It's
Oh, then it's the same as the other one. I thought you
Yeah.
said it opposite
Yep.
before.
No, same as the other one.
Okay, that's fine.
So it's 17, it really is 17 RPM, except we don't want RPM. That's where your angular speed or velocity. We want it in the right unit, which is radian per second. So how do we convert RPM? So when you look at that number, it's negative 17. The units were what? Revolution per minute. Let's see if I can change the rev to radian, if I can change the minutes to seconds. Since rev on the top, you want rev on the bottom, radian on the top. One rev has how many radian? 2 pi, right? So notice now the revs are gone. Mathematically, they cancel each other out. What do you have? You have radian per minute. You get minutes on the bottom. So you want to cancel minutes from the bottom. What do? You put minutes on the top, seconds on the bottom. 1 minute has how many seconds? 60. So what is the angular velocity? Negative 17 times 2 pi divided by 60. And I got negative 1.78 rad per second.
How is it negative 2 pi? Because going the...
Negative the direction, clockwise, that's what the negative is. Every once in a while, I don't know, you might hear the word period in math. And I'll go on the next page here. It's always given the capital letter T. And that means how long does it take for it to complete one full turn, one full revolution? And the way you find that, if you want to, the time, by the way, that's in seconds, it's T equals 2 pi divided by W. When you put your food in the microwave to heat it,
My foot?
your food,
Oh,
you can put your foot in the microwave, but good luck closing the door. So you're going to put your food in the microwave, not your foot, and you're going to heat your coffee. How is that? Or make a baked potato. You put on potato, you see the thing spinning.
Completely.
The speed that tray in the microwave spins, the speed is actually 5 RPM. It doesn't spin that fast. If you ever watch the food in the microwave, it's not really flying around, slowly. 5 turns per minute. It takes about 12 seconds for one full turn. So now, can we get what W is first? I'm looking for T, by the way. Find the period. Find what T is. I already told you it's 12 seconds, but I want to show you the math behind it. Because it's 5, this is 5 revolution per minute, right? 5 full turns every minute. So it's 1 over 5 of a minute, 1/5 of a minute for the time for one full turn. And that's why it's 12 seconds. But we'll go through the math. Now, I don't know if the microwave turns counterclockwise or clockwise. I really don't remember.
I'm pretty sure
Clockwise?
it's clockwise.
It really doesn't matter.
Depends on
No,
the
once that's
microwave.
spinning.
It'd be like this way and then that one.
And then the next time you put something else, it goes the other way.
Really?
It changes every time.
Cause it,
Really?
Yeah.
I never paid attention to that.
Actually,
I
don't
'Cause it
spin,
cranks
some
up.
don't even have it.
so we'll just use the speed anyway, because speed actually doesn't have direction. So we'll go 5 RPM. I gotta go home and watch it now. I will.
I've watched it many times.
Yeah, you have to put one in, and then take it out, and then start it again.
when you're really hungry, you don't take your eyes off that food.
Yeah.
You know which way it's going.
So it's 5 revolution per minute. That's what that means. A rev has how many radian? 2 pi. And the minute has how many seconds? 60. So if I do the math, the speed of that in radian per second, I say speed because once you say velocity is a vector, you have to give it direction. 5 times 2 times pi divided by 60. It is 0.524 roughly rad per second. So how long it takes to complete one full turn, that's the period. T, it's 2 pi divided by W. Now if we did it correctly, it should be 12 seconds.
I did doctor with me.
2 pi divided by that number. It is 12 seconds on the money. So we know what angular position is, that's theta. We know how to measure it. We know what the angular speed, how fast things are spinning in radian per second. And what about angular acceleration? Angular acceleration. For that we use alpha. And again, the unit, just like the unit for acceleration is meter per second squared, this will be radian per second squared. Accelerations change in what? Velocity over change in time.
So the calculator needs to be in radians.
Yes. Now, can the acceleration be negative and can it be positive? Alpha is greater than 0 when what? When W is what? When the speed is increasing. When something's spinning faster. And alpha will be negative when the speed is what? Decreasing. Like I'm trying to think of an example here quickly off the top of my head. Alpha is increasing. If you take a pulley and you have a rope wrapped around it, but at the end of the rope you have a little weight dangling here. And it's free to move. There's no friction. What happens when you let go of that pulley? You're holding that pulley. What will happen? Start to roll and come down. All the way down. Is the speed of this going to increase or decrease as it's coming down? Increase. So alpha will be greater than 0. Do the reverse of that. Deadliest catch. When they go and get something, they go and they attach a heavy weight, which is the weight of that all the fish in
I
it.
went on their boat when I was in Alaska.
Oh yeah? You went to Alaska? That's cool. So when this one is moving up, is the velocity increasing or decreasing? Well, the velocity of that stays the same because we have an engine that keeps pushing on it. But if something was spinning and you just grab it and put it on, let it just pull it up, you will see that velocity will start to decrease. So if somebody spun it like the wheel like really fast with their hand and put the string on it and stop spinning, as this one rises up, you will see this one start to slow down. Alpha will be negative. This one's moving down. So we pick up speed, this is going up, alpha is negative. Now, I can go and start talking about change in, if you look at that, change in W, well, that's W final minus W initial. Divided by what? Time. If you multiply both sides by t to get rid of the fraction, and what do you know? It says W final equals W initial plus alpha t. That looks like one of the equations we had before. Look at equation number 2. V final equals what? V initial plus AT. V is the same as W, except one is linear speed, one is angular speed. And alpha, this is linear acceleration, this is angular acceleration. So these 4 equations are going to be the same 4 equations here when things are rotating. The only thing I'm going to do, every time I see x, I'm going to take it out, replace it with theta. Because when things are spinning, distance we use what? Theta, not x. Speed, velocity, we don't use v for velocity. When things are turning, what do we use? W. And when you have an acceleration, when things are turning, we use alpha. If you make the changes, we can take these 4 equations now. I'm going to put them on the next one. These 4 equations I had before, I can rewrite them now, and I'll be able to use them. The first one, equation number 1, is going to say what? Theta equals theta initial plus average speed, angular speed times t. Notice I took x out, put theta. I took v out, put w.
Just do whatever you want.
Yep. Second equation, w equals W initial plus alpha t. Third equation, theta equals theta 0 plus W0 t plus 1/2 alpha t squared. And equation number 4 is W squared equals W0 squared plus 2 alpha theta minus theta 0, or change in theta. And these are the 4 equations. Same exact 4 equations we used before. So I'll put them on my yellow sheet of paper here, so in case I need them in the future. Theta equals theta 0 plus W0 t plus 1/2 alpha, not a. And equation number 4, it says W squared equals, don't move, W0 squared plus 2 alpha theta minus theta 0, or the change in theta. So these are my 4 equations. I'll see if I need them. I'll leave them on that sheet of paper. So let's see if I can apply that to some of the problems here. And my other question, do you think there's a relationship on how fast things are turning? Like if you have a bicycle, or if you have a chain, let's say we have a wheel here. On the wheel you have a rope attached like this. Do you think there's a relationship on how fast this one is turning? To if they have a rope, at the end of the rope we have, I don't know, a piece of paper, a string here, and we have a piece of paper attached here. How fast this one is moving, that's called linear velocity. Is there a relationship between this velocity, the velocity of this, and how fast this one is spinning? How about I phrase the question? How fast your wheels are turning on your car versus what's your speed on the road when it says 75 miles per hour? The faster this one spins, the faster this one's going to move. Well, by how much? Well, that depends on the radius r here. So v actually, it's equal to r times w. If you ride a bicycle, 10-speed bike, and adjustable, you have 10 speed on it, obviously. So now what happens when you change gear? You have it actually on the biggest setting there, and you're pedaling, it's really hard. Now you go to a lower gear, which is smaller, you move actually the chain to the next one. The bike is not moving as fast. It's slower. The reason, before it was sitting on that one, now it's going to be sitting on the inner one, the smaller one. The chain is sitting on the inside one, gear, and the next one. And every time you make that gear smaller and smaller, you go slower and slower. If you've gone skiing, this is the chair lift. Remember the rope on the top, there's a chair, and you're sitting in the chair, you go into the mountain. Well, if you watch that rope, at the end of the rope, it goes on a pulley there, a big disc there, and it comes back. The way they slow it down, they can't really change the size. There's only one disc. The place I've been to, there's only one round disc, and you can't make that one smaller. So the only other option to change that, since you can't change r, you lower the speed, how fast this one is turning. If it's not busy, they slow it down. I think otherwise they're wasting all this electricity for nothing. When it's really busy, they crank the speed on this one, so that chair is moving much faster. But there's definitely a correlation between these two. As the rotation is increased, the velocity will increase. If the radius doesn't change. If you start playing with both of them, they might cancel each other out.
There was a video about the skiing, how that wheel was broken and the speed was way too fast in it and they couldn't stop it. So you saw the people in the chairs come in like slamming across.
Oh no.
It's pretty bad.
Oh yeah, I can imagine. Especially when you have beginner skiers. Now, I don't know if they still even make CDs.
Yeah.
You do.
They still make them?
Bought one last night.
They do? Oh yeah, the band just came out. I forgot which band.
The Naked and Famous had their acoustic tour at the Iron Horse last night.
I think Dr. Drake also just came out with, didn't he? With the new one. But people say there are still some CDs.
Drake tonight, don't miss it.
Uh-oh.
Telling you. Midnight.
So now, find the angular speed. Let's take an example. Find the angular speed. When you hit angular, what are they looking for? Which letter? W. So that's W. I'll give you that hint there. Find the angular speed W of a CD. That the CD has a linear speed which has a linear speed that's V, equals 1.25 meters per second. Oh, I don't know why I did brackets. There's no brackets anywhere. Oh, I dropped something else. Now, when you're reading from a CD, this is not the it's not the old-fashioned way. We used to have that, the needle with the old records. You move the needle and it moves down here. Well, we do the same logic, except we don't have a needle. We have a laser beam that actually fires a beam to the CD, and if in the CD, if it's smooth, it reflects back, and there's a sensor that will read the reflection of the light. When you actually burn a CD, you put a hole in it. It's called a pit. And when the light hits it, it doesn't reflect straight down. It goes somewhere else, so the sensor doesn't read it, and that's how they know if it's 1 or 0 reflection. So if the beam is 2.5 centimeter from the center, we'll do it two parts.
So if there's a scratch, it doesn't reflect?
Well, that's one of the
You
problems.
can't
Yep.
hear it?
Yep. Reflection doesn't come back to it. Yep. And again, it really, if you look at it, you can't see with the naked eye. They put a little pit. That's what they call it, a little, like a pump, like. And when the light hits it, it reflects back to the other side, and the sensor is straight down. Normally, it's like this: hits it, bounce back. Yeah. The stealth bomber was designed on that principle. The aircraft. They want to make sure, because the aircraft used to fly like this, a smooth bottom. So when the enemy, they know they have that laser looking for them. Oh, and they have their sensor right there. So they shoot the beam up there, reflects right there. Oh, we have an incoming, you know. So now if you take this and twist it in all these directions, so when the beam hits this one, it goes that way, and they never know, actually, you can never sense the planes coming in. Yep. So assume that, so we look and find the angle if R equals, we'll do it the first time with 2.5 centimeter. And the second part, if R equals 6 centimeters. So we're not changing the speed the way the CD is spinning there. We're only changing where the beam, where are you reading it from? Are you reading it from this end or down here at the end? If you're at the end, that distance is 6 centimeters. If you're right there, the distance is 2.5. But you're still spinning at the same speed. Excuse me. So what's W? We know V equals R times W. That means from that equation, W equals V over R. So for part A, or the first one, W, I wrote V, but I changed W, equals V. What was V? V is 1.25, and that doesn't change. What was the first radius? Is it 2.5 centimeter? That's what, 0.025. And that's 50, and what's the units? Rad per second. And the other one, W equals V, which is what? What's V? 1.25 divided by what? 0.06. When you divide by 0.06, it's 20.8 rad per second. What does that mean? What's happening as you're reading, actually listening to a CD?
It's slowing down.
Well, it looks like it's slowing down, but to make sure that it's slowing down, but watch the RPM here. So as we travel from the outside to the inside, you better actually decrease the speed. This RPM, if you change that, remember, each radian, we're going to convert that radian to revolution, multiply by 2 pi. And second to minutes, that's a 60. This number is roughly about 477 RPM. So when you're reading on the inside, you're reading, actually spinning much faster. But when you're reading on the outside, This is roughly about 200, 199 RPM.
Is that the same thing for a record player?
Yeah. Yep. If you ever watch the ice capades when you go to see them and they hold hands and they're all skating, the person on the inside, you know, they go, which one moves faster? Inside or outside? Well, if you think about it, the inside versus the outside person, the outside person has to go this distance to make a full circle, where the inside person has to go that distance. So to cover that distance, you better be moving faster. To cover this, you don't have to move that fast. Well, how can they be moving fast if they're holding hands? Your RPM is the same. They're turning at the same rate there because they're all holding hands. But the linear speed on the outside is much greater than the linear speed on this one. If you happen to be here, somebody hit you, you're going to feel it. Where if you're right there on the inside and this one bumped into you, it's not that bad of it, you know. So we'll do something like that, the merry-go-round. So we have a merry-go-round, I don't know, there is. We got two people on it. We got one person riding the horse here, and one person is right there, and there's the center of the merry-go-round right here, spinning around that one. So this is child 1 and child 2, I don't know. I stopped drawing a picture of a person there. I'm giving up on that. And the merry-go-round is spinning this way. It's turning and you're on it. So the first question, is the angular speed of child 1 greater than, less than, or the same as the angular speed of child 2? Is child 1 speed greater than child 2 angular speed, or is it less than, or is it the same? What do you think?
It's greater since we just learned it.
Yep. Child, very good. Child 1, W1 has to be greater than W2. That's the question. This is the answer. You sure? I don't know. I tend to believe they're the same.
Are they the same because they're fixed?
Yep. The linear speed will be different. The angular speed for this one and the angular speed for that one, they don't have to go like with the CD. If you want to listen to it, it has to be spinning at a certain rate, you know, certain velocity. Velocity has to be 1.25 for you to hear it. They have to adjust that. This one, if you look at them, these are attached. If you put like a wire, if you put a board, tie these two kids together with the board at any given time, they're the same spot. Well, if they're the same spot on that ride, that means they're turning at the same rate. So W1 will equal W2. Second question. Is child 1 moving faster than child 2? And well, here's the question. It says, child 1 is moving faster than child 2, and hence the greater angular speed. I already told you the angular speed are the same. So we know that's wrong. Child 2 is closer to the axis of rotation, which result in a greater angular speed. That doesn't seem right either, because I just told you W1 equals W2. They can't be. Both children complete a revolution in the same time, so their angular speed are the same. Yep. If you're standing here, these are your kids, you're the mom or the dad, you're standing here. When they go around, when they come back to this spot, you're going to see both of them right there. If these guys were spinning at different speeds, then one person would be here, the other one might be down here. Now, they could come up, I mean, maybe I'm just naive. Maybe they do have roller coasters that, not roller coaster, what is that, merry-go-round, that the floor is one, just not one piece. Maybe the floor is like pieces, and they move at different speed. I don't know if I've never seen one. Anyone ever seen one like this? Where actually you start right here with both your kids, if you're the mom or the dad. Next thing you look, you see this one here and this one down there. If that's the case, then they're spinning at different rates. W's are not the same. But I never seen one merry-go-round that the floor is like all these move different direction, different speed. That doesn't mean they don't exist. I just never seen one. So I don't know if they exist. Anyone ever seen them? That's why I'm asking. So usually when they're here, they come around. The second time they're right here. The third time they're still right here. That means they're spinning at the same rate of speed. Because if these guys were turning at different rates, one will be here, one will be down there. And that's not what's happening. You say, well, but this one has to cover a bigger distance around. You're right, it does. That means the linear velocity, v, for the child on the outside is much greater than the linear velocity for this one. Because why? V for 1, it's equal R1 times W1. Look at the distance for R1 is that distance, which is bigger than the linear velocity for the second child, which is R2 times W. Since the W is the same for both of them, so the linear velocity for this one is much faster than the linear velocity for that one. But not the angle, not how fast they're turning, how fast they're spinning. And if you remember when we talked about rotation a while ago, we talked about something called centripetal acceleration, ACP. We said centripetal acceleration is v squared over r. Since v equals r times w, that's rw squared over r, which you end up with the math r squared w squared over r, which is r times w squared. That's how you calculate the centripetal acceleration. Now let's calculate with that acceleration. Centrifuge. Let me take that picture here. When you send your blood to the lab to test it, they take a sample, put in a tube, and put in that centrifuge. Those devices can spin at unbelievable rate of speed. So we have a centrifuge here. Can rotate at a speed, rotates at 11,500 RPM. That's an unbelievable speed. That's the bottom of the tube. So you put the tube in it. Usually they have them balanced tube. As you start spinning, the tubes will go to the outside like this. They spread just like any ride. When you start spinning, they go to the outside. The radius on the bottom of that tube, this is the radius, from the center, like if you visualize there's a center spinning around that radius from the bottom of the tube, the top might be closer, a lot closer than that, it's 9 centimeters from the axis of rotation. So there's two questions. Question number 1, find the linear speed, which is v, of the bottom of the tube. And question number 2, or B, find the centripetal acceleration at the bottom of the tube. If you ever see my brother's doctor, I used to work in the lab there, bring the stuff to them, put in the lab there. You put these in, and you'll see them the minute you start spinning, they go straight out. Like the tubes might be sitting like this initially. Once you start spinning, those tubes out, completely out, like this. If it's not like something like that. And if you look at the design of that centrifuge, it looks like this. It's a dome. In the middle, it sticks out because they want to give these tubes a chance to open like that. So the top, really, about the gap between them is about this much. When you think about this, this is 9 centimeters, that's 18 centimeters in the bottom. So they're going to open almost bigger than this. 18 centimeters, that's roughly divided by 2.5. That's about 6-7 inches on the bottom. The top is like this close to each other. It goes diagonal. So first thing first, if I want to calculate the linear speed, that's v. R times W. I got a problem. W is not in the right format for me. So I better go and find W. Let's go to the side. Revolution per minute. So we're going to multiply this by what? Rev to radian. 2 pi, and minute to second, 1 minute is 60 seconds. So 11,500 times 2 pi divided by 60. Ready for this number? 1,204 rad per second at a speed of 2,698 miles an hour. 2,698 miles per hour. That's how fast they're moving. So if somehow you can tie a string to the bottom of that tube, and as you go around, that string is wrapping itself around, and at the end of that string, you attach a piece of paper, you will see that piece of paper moving at that speed. 1,000, was it? What did I say? 2,698 miles per hour. Make sure there's no emergency here. Okay, too long. So now let's find what V is. R, the radius, which is what? 9 centimeters. That's 0.09. times that number 1204. Oh, that's radians per second there. So times 0.09. It's actually 242, my mistake. I don't know what was I thinking. Meters per second. That's times 2.24. It's about 500. I'm sorry, I said earlier that 2,000. No, that's radians per second. I forgot that's just W. This is V, 242. You multiply this number by 2.24. You move in a speed of 543 or 44 miles per hour.
Can you say that again?
Huh? That number was in radians per second. That's W. I thought that was V. I forgot. That was only W. I was multiplying that by 2.24 to change it to miles per hour, but it's not that. It's this number.
Change it to meters per second.
Yep. Yeah, I forgot to change it. I forgot that part. I was on the side trying to find W, and I lost track of it. But to find V, you take R times W, which is 242.8 meters per second. To change it to a speed you and I can understand, we multiply it by 2.24 to make it miles per hour, and that comes out 544 miles per hour.
0 times 404 is 108.
Yeah, get them.
What'd you get?
108.
108. How did I get that number?
Times 0.09.
0.09 times 1204.
108.36.
Yep. Don't trust me with calculators. I told you before, I'm probably the worst person with calculators on this planet. I am pushing buttons.
Here's where you were getting the number.
Yeah, that's what you're asking?
I think so.
Okay. So that's 108. And if you multiply it by 2.24, by 243 miles per hour. And the second question, what is what? Centripetal acceleration. R W squared. This will be cool to see what that number in relation to gravity. What's R? 0.09. What's W? 1204. Square it. Again, try the numbers before I screw them up. 1204 squared times 0.09. I got 130,000. Is that what you got? 465. What's the unit for that? Meters per second squared. Acceleration. Meters per second squared. How many G's is that? If you divide that by 9.8, that tells you how many G's on that system there. Divided by 9.8, you're getting roughly what? 13,313 G's. Gravity. So that acceleration on that system is equivalent to 13,300 times larger than the acceleration on Earth. And you see in the F-15 planes taking off, and they take civilian with them, and they try to play games with them. And the minute they hit 12G, 9G, 10G, they pass out. Pilot can last about 12G because they wear that special suit that holds the blood from just flowing to their head. So imagine 13,313 G on that system. There's also another relationship. I talked about V versus W. I'm almost done with this video. I'll switch. There's one that ties the A to alpha. So there's a relationship between linear and angular acceleration. Linear acceleration equals R times alpha, just like linear velocity is R times W. Linear acceleration is R times alpha. If you were holding a string, at the end of the string, you start spinning the string, and at the end there's, let's say, a rock there. So there's this, and you're holding that, that's you here. You're holding that string and you spin it. You'll see the rock is moving and it's picking up speed because you're increasing your speed. So you start first not moving really fast, now it's moving really fast. So you pick an acceleration. So this one is an acceleration alpha. What happens if that string suddenly snaps? What will happen to that rock? We'll go flying in this direction, tangential. That's your A. If it breaks right here, it's going to fly in that direction. If the string snaps right here, the tangent will be in this direction. If it snaps right here, the rock will go in that direction. So it depends where you are. But the value of A, the direction might change, but the value of A will always be R times alpha. What was the acceleration? What is the angular acceleration multiplied by R? And that's the value of the acceleration, the tangential acceleration. It's called tangential linear because it's tangent to the point where it snaps. It's always going to be tangent to it. And I've done that experiment here where I put a hole in a board and I spin it and I let go, but I'm still holding it, and you'll see it go flying in that direction, whatever direction you release it. Like some people you see them holding their keys on a chain, spinning their keys, and if on the bottom they let go, it goes that way. If they wait till it gets in front of them, it goes up in the air. If it's on top of their head, it goes behind them because it's going to go in that direction tangent. So that creates not a problem, but makes it more challenging. What does that mean? If something's spinning like this, it has a centripetal acceleration right there. So if an object here, it has centripetal acceleration, has a tangential acceleration. It also has a centripetal acceleration, which is RW squared. We call this a tangential, actually, T. Tangential acceleration. If they ask you what is A, not tangential, not centripetal acceleration, what's A? How do you find what that is? Going back to the vector chapter. On these vectors, this is the x component, and that's the y component. How do you find the result when you have the x and y component? Isn't that the square root of the x value squared and the y value squared? So if they ask you what is A, you got to do that. So it's going to be the square root of RW squared, that's it, and you're going to square that, plus R times alpha, and you're going to square that. I don't know if they're going to ask you for stuff like this. I doubt it. But just in case, I never know what our book is going to do. One of my favorite games used to be when my nephews were little. I'll take them to Westfield. There's a park in Westfield. Is it Stanley Park. And they have their little merry-go-round, and they'll sit there and try to spin them. And I'm not sure, because maybe I have a sick mind. I try to say, how fast can I spin them so they'll go flying off that? And I'll try to pick up this speed, pick up this speed, pick up this speed, pick up this speed, till finally they can't hold it anymore and they go flying off that. And they cry a little bit, and I thought it was funny. But that's because of these logics. The faster you spin them, the larger these acceleration. And the only thing keeping them actually from not sliding off that is two things. the friction force between the board on the bottom and their body. And the other thing, there's a little beam in the middle they hold on it. And when you're a little kid, how big that force is. Doesn't take much to separate your hands. You know that when you tease your nephews or your brother and sister, you can grab their hands and move them. They don't have that much force. So the faster that you spin, eventually that force is going to be so large that they can't stay on it.